In this video, we're going to go through bond polarity. Our essential question is, how does the difference in electronegativity between atoms determine the polarity of a bond? And how does bond polarity influence the overall polarity of a molecule? So bond polarity refers to the unequal sharing of electrons between two atoms in a covalent bond. It occurs when atoms with different electronegativities, which is the ability to attract electrons, form a bond. The difference in electronegativity between the bonded atoms determines the polarity of the bond. So think about the Earth, right? So the Earth has a North Pole and a South Pole. They're different. So when we talk about polarity, we're talking about poles. So we have the North Pole and the South Pole. They're different. On a battery, we've got a positive end and we have a negative end. They're different. So again, polarity refers to the unequal sharing of electrons. So they're shared differently. They're polar. All right. So as I mentioned, electronegativity is a measure of an atom's tendency to attract electrons. So we have a table of electronegativity values that we can use to calculate bond polarity. So I'm going to pull one up here really quick. And it shows all of the electronegativity values. So here we go, right here. So if you notice on the left-hand side of our periodic table, the values are relatively small, less than 1, with a few minor exceptions. On the right-hand side, the values are a lot larger. Fluorine has the greatest electronegativity of any element on the periodic table. 3.98 is the greatest electronegativity value. Okay, so electronegativity increases as you move to the right and as you go towards fluorine at the top. Notice our noble gases, with the exception of xenon, don't have electronegativity values because they're happy. They don't need electrons. Xenon is an exception. Xenon can have an expanded octet, but we don't need to talk about xenon right now. All right. If we subtract our electronegativity values and the value is between 0 and 0.4, we say the bond is nonpolar covalent. So electrons are shared equally, more or less. If our electronegativity difference is 0.5 to 2, the bond is polar covalent. Polar covalent, meaning the electrons are shared unequally. So one side is definitely going to have more electrons than the other. And then finally, if our electronegativity difference is greater than 2.0, the bond is ionic. So that's when electrons are transferred, not shared. All right, I know this sounds really overwhelming, but the good news is when we calculate our bond polarity, it's really easy. So our first example says, identify the type of bond in a NaCl bond. So we've got Na and we have Cl. So we're going to look these two values up. So Na is 0.93. Cl is 3.16. Okay, we always want to take the difference between these numbers. So we always want to subtract the big number, or the smaller number from the big number. So I'm going to do 3.16 minus 0.93. So I'm going to bust out my handy dandy calculator, and 3.16 minus 0.93, and I get 2.23. Okay, so if I go back to my table, that would definitely be ionic. And if you look at what they are, Na is a metal and Cl is a nonmetal. And we know that ionic compounds are made up of metals and nonmetals. So, that makes sense that it's ionic. All right, next example, CH. So we have carbon and we have hydrogen. Carbon 2.55. Yeah, this is literally all there is to it. You're just subtracting some numbers. Hydrogen, 2.10. So bigger number first, 2.55 minus 2.10, 0.45. Didn't even need the calculator for that one. Okay, so that means it is going to be a nonpolar covalent. So we know it's covalent because these are both nonmetals, not a metal and a nonmetal. And nonpolar means that they're sharing electrons equally. All right, now, you knew there was going to be something. So dipole moments in polar bonds. So this happens when the atom with higher electronegativity attracts the electrons more strongly, gaining a partial negative charge, while the other atom has a partial positive charge, so it's less negative. The separation of charges creates a dipole moment, symbolized by an arrow pointing from the positive to the negative side of the bond. All right, let's take a look at an example. Hydrogen and chlorine. Hydrogen is 2.10 and chlorine is 3.16. All right. So 3.16 minus 2.1, 1.06. If I go back to my table, that is going to be a polar covalent bond. So the more electronegative atom is chlorine. So I'm going to draw out this bond, HCl, and I'm going to draw an arrow pointed to the more electronegative atom. So chlorine's more electronegative. It has a larger electronegativity value. All right, I'm going to use this handy dandy Greek symbol, and I'm going to give it a negative because it is more negative. The side that is less negative is going to be our positive end because it's less negative, so that makes it positive. Okay. So that handy dandy letter that I drew is actually the Greek letter delta, but it's the lowercase version. So to draw that, take the letter S and I just continue this up, okay? Just like that. Whenever I draw that, it kind of reminds me of Captain Hook. Kind of looks like a hook, maybe. But yeah, that's how I draw that. So that is the symbol we use for partial positives and partial negatives. That's it. So anytime you have a polar bond, we always want to draw in that dipole moment. And that's it. That's all there is to bond polarity.